will present this tutorial, Data Integration and Machine Learning, a Natural Synergy, with Theo from Wisconsin. And before we get started, Theo and I want to thank the many collaborators we have who have contributed more or less to the slides here. And absolutely, we want to thank the people in this community who give us the content to talk about. Okay, so we will talk about data integration and machine learning. Let's get started with data integration. Data integration is to provide unified access to data from multiple autonomous data sources. And there are two kinds of data integration systems. The first one is data warehouse, where we build a single store to put data from all different sources into the same store at offline time. And this store can be considered as a materialized view. And so the nice thing about doing it at offline is we can apply very complex logic to solve the many challenges we need to address for data integration, and we will talk about it soon. But the challenge there is to keep the data up to date, and this is a view update problem, which is very hard. So far, data warehouse has been a billion-dollar business. And on the other hand, we have a virtual integration. So where we will query the different data sources at runtime through a mediated schema. So how many of you have used kayak.com? Yes. So that's kind of an example for virtual integration. So you fill in the form on Kayak, and it transforms it to many form queries from different airline ticket websites, and then retrieve the answer and return that to you. The benefit is it is definitely up to date, and the challenge is if you need to do anything more complex than union and rank, then it's very hard to do it at online time. So this is more about relational data so far. And when we talk about RDF data, where we have a semi-structured data in the form of triples, subject, predicate, objects, then we have different terms for similar concepts. Knowledge graph kind of corresponds to data warehouse, and it has been very successful recently in Google and Bing search, in personal assistant such as Alexa. And on the other hand, linked data is similar to this virtual integration where data is residing at different knowledge bases. And this, as far as I know, is not much of put into production yet. Okay, so why is data integration hard? It's because all of the data sources are autonomous. And so we have heterogeneity everywhere. The data could be in different formats. It could be web tables and lists. It could be DOM trees, semi-structured data. It could be texts, which contain some of the structured information hidden there. And it could even be like diagrams, which make it even harder. And this is what data extraction is trying to solve. And even when we have a semi-structured data and relational data, we can have different ways of expressing the same classes or attributes of entities. So for example, here we have, yes, this is a born, and this is date of birth. So these two terms are talking about the same attribute. So that's the semantic or schema heterogeneity, and schema alignment is used to resolve that kind of heterogeneity. So we also have different ways to refer to the same person, the same real-world entity, and we provide more or less different attribute value pairs. So this is entity-level heterogeneity. And entity linkage is used to solve that kind of problem. And finally, even after we get rid of all of the semantic heterogeneity, we could have different values. And here we have May 14th from IMDb and November 7th from Wikidata for the same person. Both are fairly authoritative sources or trustworthy sources, and we need to decide which value is correct, and that's what data fusion is trying to do, try to resolve the value level heterogeneity. So all of these components are very important for building an end-to-end data integration system. But here, let me put my practitioner's hat and try to tell you what is more important from a practitioner's point of view. In other words, if I have limited resources, limited people, and I want to build such a system, where would I invest upfront? And where would I wait? So the most kind of an indispensable part is entity linkage. This is almost, you just cannot live without it when you need to integrate data from multiple sources. And this is because different sources, they can have overlapping information about entities, and you need to align them together. And without entity linkage, you simply cannot do that, cannot enrich the information. The second part then is data extraction. And this is important when you decide to get data, for example, from the web, because most of the data from the web are either in text format or in like semi-structured format. So we have to extract the structure out of it. And this is also important if we want to reason about the descriptions of the entities. And that is kind of the text extraction as well. And after that, if I will need to pay a high price if I make some mistake, and if I want to get data from a lot of sources, not everyone has high quality, then I need to solve the data fusion problem. And I need to make sure all of the information I provide is correct. And finally, schema alignment is important in a few cases. First, it is important for relational data. And this is partially because if we have like semi-structured data or unstructured data, then data extraction is partially solving the schema alignment problem. And second, it is important when we have a lot of data sources. This is because if we have only 3 to 5 sources, the companies often want to like hire some taxonomists or ontologists to solve the problem manually. But when we have a lot of sources, we cannot do this manually. We cannot afford it. So that's kind of from the practitioner's point of view, and that would be the order that we will present these different components in this tutorial. But now let's look at the other side of the game, which is machine learning. Machine learning is to teach computers to learn with the data, not by programming, but by data. And a little bit more formal definition from Tom Michel is it is a computer program that would learn from experience with respect to some particular tasks. As we have more experience, and then the performance on the task should be better. There are 2 main types of machine learning. One is supervised learning, where we are given the data examples for learning. So we have positive examples and negative examples, and in the classification problems, if we got a new node, we try to decide if that is a positive or negative. And in the continuous space, if we know the x-axis or y-axis of the nodes, and now if we get a new data instance where we know the x-axis, and then we try to predict what is the y-axis. And certainly it can be multiple dimensions, and it could be multiple classes. The second type is unsupervised learning. So here we don't have much of examples, but we want to find the structure of the underlying data. And a popular problem is clustering. And hopefully after looking at all of this, we will put them into 3 clusters. So these are only the 2 major types of machine learning. And there are other things. And in the second half of the tutorial, you will hear like semi-supervised learning a lot. That is kind of a part of or a kind of a supervised learning, but it has a lot of new challenges. And also reinforcement learning, I guess you have all heard about it, and that is also not falling in these two categories directly. So there have been many different techniques for supervised machine learning. And here I'm putting them into 6 categories. The first one is hyperplane. And so linear regression, logistic regression fall in that category. And it is said that whenever you have some machine learning problems to solve, the first model you should try is logistic regression if it is a classification problem. And also, logistic regression turns out to be the simplest form for 3 of the other classes, like kernel, graphical, and also neural network. And the second kind is kernel, SVM, support vector machine. And here the idea is that let me put the input from the original space to some new space such that the gap between the positive and negative examples is maximized. And this was very popular about 5 to 10 years ago. The third one is tree-based models. This is kind of a reviving model. It started from decision tree, and recently it is a random forest XGBoost got a big popularity. The fourth one is a graphical model. This, again, is kind of for a long while, and we have this generative model, the Bayes net, and we have also discriminative model, CRF, conditional random field. And the fourth one is logic programming. This is kind of what our database community is familiar with. It's because the logic here is similar to the logic at database we deal with. And for example, here it is saying if A is smoking and A and B are friends, then likely B is smoking as well. But different from data log, here it is not card constrained. So for each such logical rules, we have some score or confidence or probability for it to hold. And in addition to this Markov logic net, we also have a PSL, which is quite popular recently. This is a probabilistic soft logic. And finally, deep neural network. I guess everybody has been listening, hearing this every day. And this is more of a using neural network, and including like artificial neural network, which is more feed forward, and also convolution neural network, where we are allowed to reuse some of the parameters in this network, and also recurrent neural network, where we can handle sequence of data. So I wouldn't have time to talk about all of the details, but we do have a lot of choices. So Pedro Domingo has a great paper in the year of 2012 to talk about key lessons for machine learning. And so here I'm repeating 5 of the lessons that I think I sort of like best. The first one is learning equals representation. That's kind of the model we need to use. And evaluation, what is the objective function that we try to optimize? And optimization, how to optimize it. And then the second lesson is that it's generalization that counts. Generalize beyond the training examples. It's not to predict for the training examples that we have already seen. It's more of predict for those examples we didn't see. And so avoiding overfitting is a key to success. The third one is data alone is not enough, and that's about this no free lunch theorem. No learner can beat random guessing over all possible functions to be learned. So we have to choose a model with some assumption. And the fourth one is intuition fails when we have high dimensions, and this is the curse of dimensionality. When we have millions of dimensions, something that could work well could fall apart. And finally, more data would beat a cleverer algorithm. And so a lot of recent machine learning models, they are data hungry. And it is shown that for this image recognition, after Google gave it 300 million of images, the learning curve is still not flattening. So meaning if we give it more and we can get better results. So why am I highlighting these two lessons? It's because the first one, we will revisit it when we talk about applying machine learning in data integration. And the second part basically says why data integration is important for machine learning. And we will get there. By the way, so far so good. Any question? Feel free to ask questions. We will be late anyway, so. Okay. So why am I saying data integration and machine learning are synergy? So data integration is kind of giving you data, giving you knowledge, and machine learning is kind of giving you intelligence. Just as human beings, being knowledgeable and being intelligent, these are definitely related. And similar for these two techniques, machine learning could help data integration to be more effective because it allows automation. We can automate a lot of data integration tasks with training data. And also, given the recent success that we observed for machine learning to understand text, to understand images, it is reasonably to hope it will also help us to understand the semantics from structured, semi-structured data for data integration. And on the other hand, data integration can also help machine learning because it is providing data. And it collects a lot of data that could be used to train the machine learning models. And also it more or less clean up the data that will feed more valuable data to machine learning models. So it is said that give me a fulcrum, I will move the earth. And similarly, as people from the database community, we would say, give me a data integration funnel, I will move machine learning. So there are many, many systems where data integration and machine learning, they are leveraging each other. And here, because of the time, let me shamelessly sing out one system. And this is a product graphs project that we are building at Amazon. And we can see that the goal is to build a product knowledge graph. And on the one hand side, we need to construct the knowledge graph. So we need to extract the knowledge from structured data sources, from the web, and from catalog descriptions, text, etc. And then this is more of a collection extraction. After that, we need to clean up the knowledge by applying schema mapping, entity resolution, knowledge cleaning, and this is a combination of part of the data integration techniques and part of the data cleaning techniques. So this side is more of machine learning to help data integration. And on the other side, after we got the product graph, we will use it for recommendation, for search, QA, conversation. And also we try to do graph mining to find important patterns. We try to generate embeddings for the entities and relationships in the knowledge graph and use them to support more learning. So this side, it is more of data integration to help machine learning. Okay, so far I guess I'm already spending like 1/4 of the time to go through the introduction. This is a very short tutorial, 1.5 hours. And so the goal is definitely not to present a comprehensive literature review for all topics we are covering or for any topic we are covering. And it's more of through this tutorial, we want to give you some idea about what is the state-of-the-art techniques for data integration and machine learning synergy, how we can, how machine learning has been transforming data integration and vice versa. And also we want to give you some taste on which tool is working best for which tasks. And I will let you know what is production ready and what needs more research. And then we will discuss what remains challenging, which will make researcher or scientist's life more interesting. Okay, so next we will go to machine learning for data integration, and then we talk about data integration, how that helps machine learning, and then we conclude. So as mentioned, we will talk about the 4 components in this order. And so we have a recipe for each component. We will start with a problem definition, and then we will give a very brief history. And after that, we will discuss a few state-of-the-art machine learning solutions. And finally, we will give you a summary with one short answer that you can remember and then claim to others you already know this field. So as we present all of the techniques, there are 2 themes we have in mind. The first one is which machine learning model works best. And we know that for structured data, tree-based models have been proved to be very effective. This includes random forest and XGBoost. And on the other side, for unstructured data like texts, voice, images, videos, neural network has brought a big breakthrough. And for data integration tasks, we have data in different forms. And so what is the most effective machine learning model? And the second theme is that it's supervised learning that made a big splash recently in many fields. And for many, many new models, is data hungry. However, that is very hard to just be blindly applied to data integration tasks. Why? Because our goal is to integrate many, many different data sources. And those data sources, they can have different characters of the data and have different data distributions. So the model we trained for one data source may not work well for another data source. But training the model for all of the data sources using a lot of training data, this is not scalable or even possible at all. So how can we really benefit from the recent success in supervised learning to improve data integration? So this is theme 2. Okay, let's get started with entity linkage. And as mentioned, entity linkage is trying to partition a given set of records such that each partition corresponds to a distinct real-world entity. And so here we want to decide if these 2 are talking about the same entity. So there are 3 steps in entity linkage. First, we do blocking, and this is to avoid pairwise comparison on the records, and we want to efficiently create small blocks of the similar records such that the records in different blocks are very unlikely to refer to the same real-world entity. And then we only need to examine each block and do pairwise matching. Between each pairs of records in the block, we decide if it is a match, here we have an H, or non-match. And after that, we do clustering to find which cluster corresponds to a real-world entity. So entity linkage is a problem that already have nearly 50 years of history. And the first paper was published in 1969, which is kind of 49 years ago. And at that time, for a long while, it is more of a rule-based and statistics-based methods. And for blocking, for example, we can block on records that have the same name or some other shared values. For matching, we can do average similarity of the attribute values. For clustering, we can do something like transitive closure. And actually, amazingly, the first paper is more of a statistical based. And that is kind of the very early version of machine learning. In the year of 2000, there started to be early machine learning solutions. Supervised learning has been used for matching. And so in an experimental paper by Erhard Ram, so decision trees and SVMs are compared on different data sets. And we see 90% of F measure on easy data sets and 70% of F measure on harder data set with 500 labels. And also for clustering, correlation clustering, Markov clustering, these are applied. And they are like experimentally compared in Renee Miller's experiment paper. In the year of 2015, we started seeing more supervised learning using more advanced models. So random forest has been used a lot for matching. And we have seen like F measure above 95% with millions of labels. And then so many labels is hard to afford. And so people are applying active learning, both for matching and for blocking. And in a recent paper, we see that with about 1,000 labels, we can get good results like 98% for easy domains and 80% for hard domains. And we see that this is better than these numbers. And then in this year, finally, we see deep learning solutions to solve this problem. And this morning, if you went to the Research 1 session, we have a paper presentation there. Okay, so as mentioned, because of the time, I will only talk about some very recent techniques rather than the whole history. So this is a paper about using, this is actually less of a paper, but more of a talking about how to use random forest for matching. And the features for the machine learning model is attribute similarity measured in various ways. It could be string similarity measured in Jacquard similarity or Levenstein distance, or it could be number similarity like absolute difference, relative difference. And then we apply machine learning models, and this includes logistic regression, random forest. And here is the results for a fairly easy pair of data sources, Freebase and IMDb. Both are fairly clean and fairly authoritative. And we see that this is the results for random forest when we increase the training data set size. And this is the results for logistic regression. So obviously, random forest is getting much, much better results. And when we use XGBoost, we see marginally better results. However, because XGBoost has a lot of hyperparameters, so the results can be, the model could be quite sensitive in terms of the training data. If the distribution is a little different, then the performance could vary. And on a harder case, we have experimented between IMDb and Amazon Movies, where the data is more noisy. And with 200,000 of labels and 150 features, we see this is the PR curve where the precision is 0.98 and the recall is 0.95. And in my group, I have some scientists, whichever data set you give them, they can come back with linkage results with above 95% of precision and recall. So this is pretty much production ready, except that, yes?
This is just the primary matching, right? One entity to another, right?
Yes, this is pairwise matching. Yes. Attribute matching. So the pairwise matching is based on attribute similarity, but it does not match the attributes. Yes. Okay. So in terms of the performance, it is already ready for production. However, it requires a lot of labels. And we have been talking about 1.5 million of labels or 200K labels, and it is very hard to collect so many labels. So there are results about using active learning. And Magellan, this is the Magellan paper, and it shows that with just 1,000 labels, when we do active learning, we can get quite high precision recall for various kinds of data sets. And in addition, from our side, we also did some experiments. An intern student last year adapted this uncertainty sampling method for active learning, such that we can get precision and recall of 99% by reducing the number of labels by 2 orders of magnitude. And then now we only need about 10,000 labels to get this very high precision and recall and to put it into production. So starting from this year, as I mentioned, there have been this deep learning solutions. And this morning, we have heard the solution from the Wisconsin team, which is also part of the Magellan kind of a toolkit. And so it applies bi-directional recursive neural network and combined it with attention. And for all of the attributes, note that instead of saying, okay, I will compute the attribute similarity using Jacquard or using Levenstein, it tries to learn how to compute the similarity by first generate a summary of the attribute values and then generate the comparison. And we got similar performance for structured data. However, it is significant improvement on text and dirty data. So if you haven't listened to the talk this morning, you are welcome to, oops. Where am I? Okay, to come to the poster session on Wednesday. And there is another deep learning model proposed, and that is borrowing the idea for knowledge graph embedding. And so it generates in the embeddings for the entities as we do in knowledge embedding and compare two entities on the embeddings. So this is the super complex model, which I will skip. And the key message from there is the performance is better than previous knowledge embedding methods, but it cannot compare with random forest. However, the promise there is that it enables linking entities of many different types. So we do not need to train a model for every type. So far we have seen these techniques, and some of them seem to be fairly mature. However, we have been talking about 2 sources and 1 type, using a lot of training labels to train the model. And in general, we could have multiple different data sources, we can have multiple different types, and we can have the data changing over time. So how can we obtain abundant training data for all of this big complexity? That's the big problem to study in the future. So a very short summary. Entity linkage is to link references to the same entity. And random forest with the attribute similarity as the features is pretty much production ready and is used in industry. Deep learning has been applied to handle text and noises, but we still need some end-to-end solution for future work. So far, so good? Okay. Next, let me talk about data extraction. And here we are trying to extract a structure from semi-structured or unstructured data. And the structure could be in entity attribute value triples. It could be is a relationship, or it could be events with multiple arguments like who, what, where, when. And in this tutorial, we will focus on semi-structured data. This is partially because of the time. I once presented something like 20 papers in 20 minutes. That's only about texts, but today I'm going to spend only 12 minutes here. And also, we have another good reason why we will consider only semi-structured data, and I will present later. So there are 3 types of data extraction. Closed word extraction, that's kind of my name for it, where we only extract things for existing entities and attributes. For example, like the entities we extract, they have the IDs in some underlying knowledge base or references, and the place of birth, which is the relationship, is in the schema. The second type is closed IE. So here we also only consider existing attributes, but we extract new entities represented using strings. So only with this, we are able to extract information about not that famous people like me. And the third type is OpenIE. So this time, not only we are not limited to existing entities, but also we are open to the attributes. So for example, we have was born in and is originally from, and they actually express the same meaning, but we just use the text from the data sources. And this allows us to get a lot of new relationships. Okay, so why? Wait a moment. What happened? Let me see. So they know you want to listen to it again. So go back all the way. Okay, so in this talk, we will focus on closed IE, and this is so far the most popular work. And data extraction has been 35 years. The early work that is famous is kind of a Hearst pattern to extract is a relationship. And then we have IBM System T, which is also rule-based. But there are also some early machine learning models to extract is a relationship and events. And in the year of 2005, we started seeing a lot of work for relation extraction. That is to extract the subject, predicate, object triples. And so there, we first do named entity recognition. Given a sentence, we find out the two phrases talking about entities. And then we do entity linking, linking the phrases to some underlying entities in the knowledge base or in Wikipedia. And finally, we do relation extraction to figure out the relationship between the two entities. And there are two major families of models. One is feature-based, which considers semantic features, syntax features, and lexical features using logistic regression and SVM. And later on, there is kernel-based methods using SVM. And because it is kind of hard, one challenge is to get all of the training data for it. So distance supervision is invented to solve the training data problem. And also another challenge is to extract new relationships. And the OpenIE is proposed to solve that problem. In the year of 2008, there started to be a lot of semi-structured extraction work, and including web tables, which are used to support search extraction, and also extraction from DOM trees, which is called wrapper induction. And starting from 2013, people are using deep machine learning to solve the extraction problem using all of the advanced neural network attention techniques for relation extraction. And people are revisiting DOM extraction, and also data programming, heterogeneous learning. These are invented to further solve the lack of training data problem. So as mentioned, we will focus on semi-structured data. So we will focus on these three bullets. But why semi-structured data? This is kind of convinced or motivated by an observation on the Knowledge Vault project at Google. And there, the goal is to extract from all over the web. And we see that from 4 types of data sources: free texts, semi-structured DOM trees, web tables, and web annotations, which is in the HTML according to schema.org. 80% of the extractions are from DOM trees. We see that we have 2 extractors. Their accuracy is about 0.6, which is not perfect, but at least it is better than text extraction, which is 0.5. And the early work to extract semi-structured data is wrapper induction, and so that we highlight those strings on the semi-structured data sources saying this is title, this is genre, this is release date. and then it will learn a way to extract all of the relationships. And the solution is basically to find the XPaths from the DOM trees. Why is this hard? It's because of the variety from page to page, even in the same website. So here we have like 2 XPaths for acted in relationship from 2 different pages. And you see that the index here are different. And you might be considering, okay, let me just use star for these 2 indexes. However, this XPath will give us the producer of relationship from the first page. So it's not that easy. So this vertex wrapper induction method, it will basically first cluster the web pages into clusters that each one corresponding to some template. And then it identifies the representative web pages for each cluster and asks for annotations from kind of a manual work. After that, it learned the XPaths using some simple logistic regression learning. And then it generates a whole bunch of XPath rules which can be used to extract from new data sources. So these are the example XPaths we are learning. So we see a lot of stars, and those to ensure high recall. And also we see this various constraints which can ensure high precision. So annotation-based extraction has high precision and recall, and we will show some experimental results, but it does not scale up because we need to annotate per cluster, per website, and it cannot scale to the whole web. And thus, people are using distance supervision extraction, where we use some seed data to automatically generate the annotation, and then use the noisy annotation for training. There are a bunch of systems on that. And let me just very quickly say what we mean by distance supervision. So this is a seed data from Freebase that we have. And this is our corpus text. So from the first sentence, we identify Bill Gates and Microsoft. And we know from Freebase that there is a founder relationship. And so we assume this sentence is talking about the founder relationship between the 2 entities. And this gives us some feature. So I wouldn't go to the details because of the time. And then now let's consider how we might apply this on semi-structured data. On semi-structured data, we don't have sentences. So the unit, the annotation unit, is not a sentence, but the whole website, or web page, sorry. And that makes the annotation to be very expensive and error-prone. And what we did, among many things, is that we split the label generation into 2 steps. In the first step, we identify the entities, which is the subject of the web page. And in the second step, we annotate the relationships. And we use that to do training and to extract more triples. So at some experimental results, we see that this solution is getting very high precision recall on a benchmark data called SWDE. And sometimes it even gets better results than wrapper induction, which is manual annotation based. So we run it on 33 websites, and we can see that we can extract with a precision of 90%. And we got a lot of new entities. This is to compare with the state of the art, where we used to have 60% of precision. Which model is the best? Logistic regression amazingly performed better than random forest on this, maybe because of the number of features we have. And the deep learning is whether that is good enough for this. It is still a question mark. And the reason is, if we look at the web page layout, it's neither like a 1-dimension sequence or regular 2-dimension grid. So CNN or RNN, it does not apply directly. There has been some early solution towards this goal, and that's the fondue system. And we will listen to a talk on Thursday. And so I won't spend much of time on this. And I will skip web tables. And the challenges here in applying machine learning on data extraction is the automatic data extraction still does not reach the production quality. So how to improve the precision, that's still a valid research problem. And every web designer, they have their own whim, but there are some underlying patterns that as human beings, we can tell what is attributes and what are values. So we should think about across different website learning. And finally, closed IE so far are throwing away too much of data. And how can we even apply OpenIE on all kinds of data, including semi-structured data? Very quick recipe. So data extraction is to extract a structure from semi and unstructured data. Wrapper induction has high precision recall and is production ready. And distance supervision is critical for collecting training data. And logistic regression is surprisingly effective, but more research is needed for deep learning. Okay, next, Theo. This is not easy.
Yeah, I won't use one. Awesome. Thanks, Luna. Okay, so we will continue with the next steps in data integration, and then we're going to switch to how data integration itself can help machine learning. For the interest of time, we will skip schema alignment and we will go directly to data fusion. So what is data fusion? So Luna so far talked about the fact that you want to identify if two different records talk about the same entity. You want to be able to extract information from unstructured data. The whole idea of data fusion is that once you've done that, once also you've aligned your schema and so on, you want to be able to resolve conflicts in your data, and you want to find what are the true values describing a certain entity. For example, if you actually go on Google right now and you ask, what's the length of the Mississippi River, I dare you to actually go and find the true value. According to Knowledge Graph, you cannot see the value there, but it's 2,320 miles. If you go on this official government webpage, you have 5 different numbers. And if you go on this web table in Wikipedia, you have yet a different number. So which one of those is correct? So let's see a little bit the setup, the basic setup of data fusion, and what you can do to automate this process of actually identifying the true values for different attributes of different entities. So what's a basic setup? So the basic setup is that we have a bunch of data sources, and they provide observations or about different facts. For example, you can see on the left that Wikipedia says that the length of the Mississippi River, so the fact here is the length of the Mississippi River, and then the value for that fact, according to Wikipedia, is that it's around 2,200 miles, right? You have a bunch of other sources providing you information about the same facts, and now you can see that you have, in certain cases, conflicting values. For example, from this other website, USGS, you actually have a value that is more than 100 miles. It has more than 100 miles difference. And now the setup, the actual goal, is you want for a bunch of true facts. So here we really want to know the true length of the Mississippi River and also the true length of the Missouri River, which is another entity mentioned in our data. We really want to find the unknown, the latent true value for these facts. So what can we do? Well, the basic idea is to actually use redundancy here. As you can see, we have a bunch of different observations about the same entities. And the idea is to use redundancy to infer the true value for each of those facts. So what is the simplest algorithm that comes to mind? What would you do? Majority voting, right? So if I am to take the majority vote, I can actually find the true value for Missouri, right? I have 2341 appearing twice versus the other value appears only once, right? I can find that. But I cannot do the same thing for the Mississippi River. So majority voting is a great heuristic. It works very well in many practical scenarios, but it suffers from many limitations. And just to give you an idea of what is a major limitation, imagine you have a bunch of web sources. They're all copying from each other. Can you trust the majority anymore? So if the majority colludes, you cannot really trust it. And how can we get away from this limitation? The basic idea is to model how sources generate these observations, and model also how different sources, how accurate they are at presenting different observations. So this has been a very old problem as well. As you can see, all problems in data integration are very old. One of the first papers that started studying this problem was actually published in 1979 in the context of merging or fusing observations from different medical doctors about patients. So that model is basically, it's a modern view of statistical learning, if you will, not machine learning, but it relies on a naive-based model and tries to model the error rates of different sources. Later on, we actually saw a bunch of different domain-specific strategies coming up around 1996, where you wanted to capture domain-specific information, like, okay, my sources may provide information at different points in time, so I want the most recent value to be the one that I trust the most. So you have a bunch of different rules. Later on, you try to come up with, there's lots of work on trying to encode all these specific rules and domain information into probabilistic graphical models that try to blend basically the initial statistical model together with domain expertise to overcome some limitations that we're going to see for this first model. And finally, there is some work that slowly started coming up with using, again, deep learning models for the problem of data fusion. So let's start a little bit with the basic probabilistic model for data fusion. Remember, we want to go away from majority voting and try to model the accuracy, the quality of the different data sources. So if we want to build a probabilistic model, the first thing is we need to define what are our random variables. So our random variables here are basically this latent truth of the different facts we have. Remember, we want to find the true unknown length of the Mississippi River. That would be a random variable. What are the features? The features are nothing more than our observations coming from the different sources, right? And each source now, if it gives a specific assignment to this random variable, I'm going to use the term, it supports that specific value. So it supports that the fact should have, that random variable should take a specific value. And what are the model parameters? Well, for each of these features, for each of these votes, if you will, of the different sources, you basically have a weight that is related to the reliability of the source. So if you want to see the actual model, just focus on this part here. Forget the rest of the math. That is nothing more than really a weighted majority vote, where now for each of my Boolean features, does a source vote in favor of a specific value, I just have a weight that captures the reliability of the source. Of course, if I want to give semantics to these weights, I can have more involved formalisms that reason really about the different error rates, where the error rate is defined as the probability that basically a source will confuse between value v prime for v, and so on. So this is a very simple probabilistic model. If you are familiar with logistic regression, this is actually an instance of logistic regression with Boolean features. All you need to do is give training data to this model, and you will immediately have the parameters of the model. There is a catch, however. One question that you need to ask always is how much training data do I need to get the correct parameters of the model? And there is a theorem from statistical learning that basically says that the number of training examples you need is basically proportional to the number of informative features that you have in your model. In this case, the number of informative features, remember that our features correspond to votes from the different sources. What if I'm in a web scale setup, right? Where I have millions of data sources. Do I need millions of training points? So this supervised, naive at least supervised approach here doesn't really work. So what can we do? Well, I'm going to talk about two ideas. The first one, and it's the most prevalent in the literature, is, well, we're going to leverage redundancy in a more clever way and go for unsupervised learning solutions. So this is actually what the very first algorithm did, the David-Skin algorithm. So what that algorithm does is it follows an iterative process that is it's similar basically to expectation maximization for those of you that are aware with that algorithm. Roughly what it does, it starts by a guess. So you use majority vote to actually infer the true value of this latent fact. So you make a guess. And you use that guess as ground truth to estimate based on that the error rates of your sources. Once you have an updated estimate, you actually run inference again to find new, better, like new improved estimates about your inferred true values, and you keep iterating until you converge. If you're familiar with notation from graphical models, the algorithm I'm describing is really nothing more than unsupervised learning over a naive Bayes classifier. Now, for this algorithm to work, there are very strong assumptions that need to hold in practice. We really want that, imagine that you had sources giving you Boolean labels now, 0, 1. I don't have categorical random variables, but I have just Boolean random variables. There, I require that the average accuracy of the sources is above 50%. It means that I'm not in an adversarial scenario where all these sources are really trying to vote to trick me. Not only that, but you require that sources are basically independent. You require that errors of these different sources are uniformly distributed across different instances. And really, to recover correct estimates, you need kind of a dense problem. If you have a source providing, if you have for each object a couple different sources providing you with information about that object, you really cannot find correct estimates. So how do we address these limitations? There's lots and lots of work that basically try to extend this basic naive Bayes model with more involved models that follow a very simple idea. We really want to inject domain knowledge. This is the way that you go away from not using training data. You want to inject domain knowledge, and the domain knowledge here has to do about modeling the observations of sources, how were they generated, basically how do different sources inject noise, and do different sources interact with each other? Are they correlated? So you started having models like the one shown here. This is from a VLDB paper in 2012. It tries to relax the assumptions of the initial naive Bayes model that we mentioned by here trying to relax the assumption of uniform error for the different instances. So it tries to model the prior truth probability. However, it does keep the same parameters for the source quality, and it really focuses on instances where you have a bunch of different facts for the same entity. Now, this model was just one of the first ones. You have more involved models. For example, this one here was used by Luna to estimate the trustworthiness of different web sources, which is very different from PageRank, if you will. Think of a gossip website. Its PageRank might be quite high, but the trustworthiness is questionable. So the idea there is that the source itself might not be trustworthy, but on top of that, if you're performing data extraction, your extractor might also introduce errors. So really there, you want to model your process. You're injecting domain knowledge saying that, okay, I have some quality measures for my source, but at the same time, I really want to understand if my extractor is performing well for this specific data source. And more recently, so these are models from the database community, and now you have these two that are models from the machine learning community. This is two models from an ICML paper from 2016 that really tries to model noise in collecting what is called weakly supervised training data. All these models do, they're quite complex. Don't try to interpret these diagrams. All I want you to know is that what they're trying to do is model dependencies across different sources. So the whole idea there is that we inject to relax these assumptions of the very first model that we had, is actually to go and inject domain knowledge in how we model how noisy observations are generated from the sources and how sources interact with each other. do these models perform better than majority voting? There is this very nice survey paper from 2014. All the models that you see down there labeled as Bayesian, they basically correspond to different probabilistic models that I just described with probabilistic graphical models at their core. And they really capture exactly this notion of source quality and how noise is injected. So if you see the numbers, they actually give you way more precise results compared to more naive models that either use majority voting or try to model the trustworthiness of sources in a non-probabilistic way. So the whole idea here, the main takeaway, is really you need to model the quality of your data sources. And there are a bunch of different ways to do that. Now, we talked about probabilistic graphical models. We talked about the simple naive-based classifiers and logistic regression. Where does deep learning fit here? Again, this result comes from another ICML paper that shows that the very first model from 1979, the David Skin model, corresponding to a simple naive-based classifier, is equivalent to what is called a restricted Boltzmann machine. For those familiar with that, this is probabilistic graphical model from the exponential family. The authors actually showed mathematically the equivalence of the two models so in one layer restricted Boltzmann machine is exactly the same. This is a generative model again. You find the parameters in an unsupervised fashion, and it's exactly the same as the model from 1979. But there is a key idea here. The moment you realize that just one layer from a deep network architecture, just a fact, so restricted Boltzmann machines were a very popular deep learning architecture in the past. And by past, I mean 2016. This is eons in deep learning time. Okay, but once you realize that a single layer of this network corresponds to and does exactly the same thing as this statistical model that you had, well, what you can do is you can put your deep learning hat on and start adding layers. And the moment you do that, the authors show that actually what starts happening is you capture correlations across sources. So now you don't need to model explicitly behaviors like copying, you don't need to model explicitly behaviors like collusion, but immediately through the use of a deeper network, you can actually capture correlations of different data sources. So this is one direction where deep learning comes into data fusion. However, there are more recent directions, for example, that of knowledge graph embeddings. So this is a survey that actually doesn't talk about data fusion, but gives you a high-level idea why a knowledge graph can actually be represented as a tensor. Tensors are the fundamental units of deep learning. So why a tensor? A knowledge graph is nothing more than a collection of triplets of a subject, an object, and a relation between them. So for example, here, what you have is that Obi-Wan Kenobi is actually a character in Star Wars. So you have these two entities, Obi-Wan Kenobi and Star Wars, connected through the relationship character in. Well, it's very easy to see that actually that corresponds to a point in this three-dimensional space where in 2 dimensions I have my entities, the third dimension is basically the different relations I have. And now if you want to capture that distribution, all you need to do to keep a smaller, a denser representation is just to perform a tensor decomposition. So the highlighted parts here, what you really learn is a representation that captures this knowledge graph. Why not take this step a little bit further, right? If I have these latent layers, basically, that capture my knowledge, why not use deep nets to actually get more rich representations that I can use? So this idea has been used. I encourage you to actually read this survey paper by Nickel et al. To capture embeddings of knowledge graphs. And more recently, it has been used to actually learn embeddings from different data data sources. For example, you have a bunch of collections of entity relation mentions from IMDb. You can embed those in this low-dimensional space and use that to identify if you have erroneous triplets from another data source. Okay, so this is the state of the art when it comes to using unsupervised techniques that are related to deep learning in data fusion. But let's take a step back. Let's go back to our initial question, which is, I cannot get training data. I want to limit I need to limit the amount of training data required by these approaches, right? So one direction we saw is, okay, I'm going to rely on redundancy and not use any training data, so I'm going to be in an unsupervised setup. The other idea is, okay, that theorem tells me that my training examples should be proportional to the number of informative features. Let's reduce the number of features. How can we do that? Well, the key idea here is to realize that sometimes we talk about the authoritativeness and the error rates of a source, and we tried to inject domain knowledge in how noise was injected from the different sources. But in many cases, I can take exactly the same rationale and convert it into a feature engineering task. I'm going to say that the accuracy of different sources depends on specific, domain-specific features that characterize their trustworthiness. For example, if you have web-related data and you have a website that corresponds to a newly registered domain that is similar to an existing domain, that was actually a prevalent example with the fake news boom, right? Or if I have traffic statistics, there aren't that many users, or whoever visits that website, they actually leave immediately. Or if I have text quality features, for example, if you see some of the highlighted words there, they're not the best that you can use to describe people, right? These are hints that the source should not be trusted. Similarly, if you're in a crowdsourcing setup, you have a bunch of labelers, and you know, for example, that the tasks you submitted require 30 seconds for annotation, but you have a worker that submits answers every second. Probably these answers won't be they won't be of high quality. So you can take these domain-specific features into account, just extend your initial logistic regression model that we saw with these features. What you achieve here is basically you reduce the dimensionality of the learning problem you have, and with very few training data, you can actually perform much better than state-of-the-art probabilistic graphical models that encode the same domain expertise. One thing here, I haven't mentioned the magic word semi-supervised learning. So we use that training data, the small amount of training data as a seed, and again we exploit exactly the same powerful representations that these unstructured, unsupervised models have to actually obtain better results. So one thing to remember here is that we have representations that allow for efficient, effective, semi-supervised learning. So this is actually the state of the art in data fusion. These two parallel thrusts represent the state of the art in data fusion. Now, what are the challenges? What are some challenges that need to be addressed for this to be production ready? As Luna was saying, the other parts of data integration are production ready. Data fusion and data consolidation, how to find a single correct attribute value representation for an entity, is a very challenging problem. Well, first of all, if we are to focus on unstructured data, there are only very few solutions. Everything I talked about was really relational data. If I want to apply, imagine you have descriptions of products, right? And you want to find a single description that captures all the information contained in multiple variations of your product description. There is only a small amount of work on fact verification, which is a problem related to data fusion, but we really need new models to actually address the problem of data fusion for unstructured textual data. Another idea is exactly semi-supervised learning was actually has shown positive evidence that it can significantly improve the quality of data fusion models. And the whole idea is how can we actually go and collect training data more effectively? The previous model I showed you requires that you go and manually specify domain-specific features that describe the accuracy of the sources. This is clearly not a scalable solution for production, but the key idea there is that it allows you to exploit semi-supervised learning. And finally, when it comes to deep learning and representation learning, we only talked about embeddings in a graph-specific space, or we talked about models like restricted Boltzmann machines that I dare you to try and scale. So we need new representations. We need to understand how we can combine semi-supervised learning with new deep learning representations. So what is the main takeaway? What is the recipe for data fusion? Well, again, remember the definition is I really want to resolve conflicts and obtain the correct values for the different attributes of different facts related to entities. And what I encourage you to take away from here is that you really need to reason about the quality of sources, meaning you really need to reason about how noise is injected, and you really need to reason about the correlations across data sources. Semi-supervised learning has the potential to improve the quality of existing solutions, but we really need more work on designing models that can actually leverage the power of semi-supervised learning in these setups. So any questions on data fusion? Okay, so let me recap what we saw for the first part, which is how machine learning can actually help data integration tasks. So in summary, we've seen that for so data integration contains, is basically a collection, an umbrella term for a bunch of different tasks: entity resolution, data fusion, information extraction, schema alignment. And we have a collection of different models, different machine learning approaches that have been applied to different models. And in fact, you cannot really find a single winner. But if you try to abstract what is happening across all these tasks, you can see that ensemble models, either random forest that Luna mentioned, or these types of probabilistic graphical models for merging the observations of different data sources, they are also a type of ensemble models. And then deep learning models, they show promising results for streamlining some of the tasks in data integration. Of course, there is more work that we need to do. And the question is, the second question we need to answer is supervised learning the solution here? Clearly not. For many of the tasks, when you ask for industry and for many companies, it might be possible to get millions of labeled data. But for example, for domain scientists, for medical doctors, right, you cannot ask them to go and label this much data. So you need to employ semi-supervised methods and weak supervision methods. The problem again here is, yes, we did use machine learning models to solve the problem of data integration to a certain extent, but we require that we need lots of data to feed into these models to solve the problem of gathering data. So we are kind of stuck in a loop here. Now, that brings me to the second part of the tutorial, which basically I'm going to describe how to get away from that loop, how to find solutions, how can we use data integration-based ideas to actually gather this valuable training data for machine learning models, and how to actually get high-quality training data. So I'm going to talk a little bit about training data creation and data cleaning. So as Luna mentioned, machine learning is data hungry. How many of you have seen this graph coming from NVIDIA? So back in the old good days, if you see, databases are here. Purchase details, purchase record, payment record, support contacts, etc., in the gigabytes. Transactions, down here. Then we start increasing, the workloads start changing. We go into search. This is the boom of Google and the web. And then we go to mobile, and now we are in this era. We have sensors, we have natural language processing, we have video, we have cyber security logs, we have machine data, name it. The amount, all these applications are powered by machine learning, or if you will, AI. It's more sexy now, AI models. So the whole idea basically is that successful machine learning requires collecting vast amounts of data. It's a dark secret that you need one of these to get your machine learning model to perform very well. You need large collections of manually curated training data to make progress. And the key here that I'm going to focus on this part is this phrase. So first I'm going to talk about training data, and then I'm going to come back to manually curated. So for training data, we need to look back to the history of artificial intelligence, and the only reason I'm using artificial intelligence here and not machine learning is just to include the rule-based approaches. So when artificial intelligence started, we had these expert systems, right? We had manually curated knowledge being represented as a collection of rules, and you had inference engines. Do not think of probabilistic inference, but think of prolog programs, evaluating these rules, and there was no support for high-dimensional data. You had no way to analyze images, you had no way to analyze signals, and so on. Later on, in the 90s, you come up with features. People started having these low complexity models like support vector machines, logistic regression, and so on. The whole idea there is that you started using training data, but at the same time, you had to rely on feature engineering to get models that were performing quite well. And exactly because you were relying on feature engineering, basically you were fine-tuning how domain expertise was captured by your model, you didn't really require small amounts of training data. So you didn't require large amounts of training data. Some training data was enough. Later on, in around 2000, it shouldn't be 2009, it should be around 2000, we go into graphical models and logic. So graphical models, instead of reasoning about individual examples and individual random variables, we start reasoning about collections of random variables. We start reasoning about how different random variables interact with each other, and basically Markov logic networks pop up. We start blending those with databases to make them faster, and start reasoning about probabilistic inference engines. And then in around 2010 and so on, representation learning comes into play. Now, what is the main pain point in this era that we are in, the era of representation learning and deep learning? Well, you have basically these three steps. You need to collect data, you need to label data, and then you run your favorite deep net. The main pain point here is exactly how to label training data. Most of the time is being spent here. And what are the challenges now with training data? Well, there are a couple of things. First of all, collecting training data is extremely expensive. And it's a very time-consuming process. The other problem, and in fact, there is this very recent paper by Ben Recht that came out on Archive, and it's a very interesting read, is at the moment we start labeling data, we're actually overfitting to our hand-labeled examples. He talks about CFAR10 and how the different models, the moment you collect new images that are in the same family of the CFAR10 images, your models do not generalize. So hand-labeled training data do not change. The other idea is that training data is basically now the new point to inject domain knowledge. You lost with the new representation learning techniques, you've actually lost your power of feature engineering to a certain extent. And modern machine learning, as I said, is too complex to actually go and hand-tune all these different layers and how they interact. The only way to inject domain knowledge is through your training data. So the big question here is, how do we get training data more efficiently? And that leads to the rise of weak supervision and ideas like semi-supervised learning that we've already mentioned. So the definition here is that weak supervision is nothing more than a new supervision scheme, but instead of having access to gold ground truth labels, you actually have access to much easier to collect, noisier labels. And basically, it's closely related, again, to semi-supervised learning and ensemble learning. Some examples that are actually, for me at least, the three most distinct paradigms of weak supervision. The first one is crowdsourcing, where instead of having a single human annotating your data, or a team, you actually try to distribute this task across cheaper annotators. Then you can use techniques like distance supervision, where you can use curated catalogs, so you exploit the effort put by other humans in the past to actually train your system. And something that is more recent, and in my opinion, it's actually kind of the future, is to actually capture domain knowledge through small programs that you can run against a corpus of unlabeled data to generate lots and lots of training examples. So if you don't believe me, you can actually believe Luna's boss. This came from Jeff Bezos, saying how semi-supervised learning led to reduce the needs for training data by 40 times. Okay, so let's dive a little bit deeper into the rise of weak supervision and these techniques. And I'm going to point out for some of these techniques on weak supervision how data integration is actually related to them. Okay, so first one, crowdsourcing. There is this paper that talks about how can you learn from noisy crowdsourced labels. And the whole idea there is that instead of running supervised learning over gold ground truth, one has only access to multiple annotators that provide possibly noisy labels. So you have no gold standard, basically. And your task is now not like in data fusion to actually find the correct label. You don't care about that, but you really care about just training a classifier from these multiple noisy labels. As we're going to see, it's closely related to this initial Day-with-Skin model, but it has this basic difference, that you really need to learn a classifier. You don't care about the actual performance of the different annotators. That comes as a byproduct of your approach. So what is the task? I'm going to go over this very quickly. Think of binary classification. I have a bunch of examples with features, xi, and I have a label for each one. But now I don't have a single label. I have a collection of noisy labels, right? And they are provided by our different annotators. Now, the number of annotators here for simplicity is fixed. What I'm going to do, I'm going to follow the same idea and the same principles that we talked about noisy observations in the data fusion setup to model the sensitivity and specificity of my annotators. And then I'm simply going to extend a naive Bayes classifier to take into account the performance of these different annotators. Don't try to parse the equations. All you need to know is actually see that I'm not only modeling the performance of the annotators, but here I'm learning directly this vector W is the actual classifier, the actual model I want to get out of this scheme. The algorithm to train this model, again, an expectation maximization approach, a little bit different than the original algorithm, but following the same principles. So crowdsourcing is close to Day-with-Skin. What about this other paradigm, distance supervision, right? The goal here, again, is to extract, it has been applied in most cases in extracting structured knowledge from text. And Luna mentioned already, gave you an example. The hypothesis is that if I have a curated catalog of two entities being related, if I find an instance of them in a sentence, that sentence should contain some features that characterize this relation. What are the benefits? Well, the benefits is that this catalog that I'm using is actually binary curated. It contains reliable data. And the other, but at the same time, I don't really need to spend additional effort. I leverage the effort that others have put into creating this catalog. So just remember the setup that we saw before. Now, why is data integration related to this? A fundamental task while you're performing distance supervision is to actually map the content of a knowledge base to your corpus. And in fact, this problem of entity linking is inherent in distance supervision, and it can actually affect the quality of matches that you get, and it affects the quality of training data, basically, you get for your downstream algorithm. So these are some results from the canonical distance supervision paper showing the quality for matches with respect to different matches for different types of relations from freebase. So that brings us to the last paradigm of weak supervision. What if I want to combine crowdsourcing, distance supervision, and a new way to inject domain knowledge? This is the paradigm of data programming. This is very recent work that started in 2016 at Stanford. And the whole idea is that you allow users to just write small snippets of code that capture their domain knowledge, and you can apply them directly to your corpus to annotate and create training, to annotate your corpus and create training examples. Well, these rules might be noisy, right? In a similar way that distance supervision could be noisy, in a similar way that some of your labelers from a collection of crowd workers can be lazy, the same thing with this part of the code. So the whole idea is once you have this collection of diverse labels, you use a generative model to do what? You need to model how these labeling functions generate, annotate information, how they inject noise in certain cases, and how they are correlated. Does it remind you of something? Data fusion models are closely related and basically leverage this model is closely related to, again, the models that we talked about data fusion. Once you have that, the trick is to actually go and change a little bit your underlying model that you're training to be aware of the fact that your annotated examples do not have a gold label. They're not, for example, for binary classification 0 or 1 with a confidence of always 1, but they could be 1 with confidence of 90% and 0 with a confidence of 10%. And there are lots of applications for this type of supervision. Some of the most interesting results that the Stanford team had seen is that just by using Snorkel on knowledge base construction tasks where you didn't have any access to knowledge bases, curated seed knowledge bases to use for distance supervision, you can actually get really, really high, really good results, very highly accurate extractions. Now, if you want to actually have the person that created Snorkel in your team, just a plug, an advertisement, Alex Ratner is behind the Snorkel framework. He's on the market this fall. Feel free to reach out to him. And if you want to talk to him actually during this conference, you can see his talk about what's next with Snorkel on Friday. Now, what are the challenges, just to wrap up this part, what are the challenges when it comes to creating training data? Well, I talked about crowd workers, I talked about distance supervision where you have basically the content of different knowledge bases being matched to sentences. And I talked about writing pieces of code that will annotate your corpus. A big challenge here is how to deal with richly formatted data. Weak supervision, when you have information that can include images, text, tables, video, it's not really well understood yet. We have some initial results, but we are not there yet. The other idea is, can we actually combine, how can we combine in a systematic way weak supervision with other data enrichment, if you will, techniques like data augmentation? There is this very interesting work in the area of data augmentations that describes how you can perform transformations to your initial training data. More recently, there is some work by Google describing how you can cast this as a reinforcement learning problem to actually enrich and augment the training data that you have. And in a similar flavor, how can we combine weak supervision with semi-supervised techniques more closely? There are some obvious connections, but not all types of semi-supervised learning can be cast directly into this weak supervision framework. And finally, what do we do about relational data? In text, it might be easy to actually define certain invariances, certain phrases that reveal relations between entities. For relational data, we have some initial results, but it's not clear how you can do it. So just to recap, you want to go beyond gold labels. You want algorithms, you want machine learning models that start using that can use noisy training data. And the short answer here is there are lots of techniques that are related to data integration, leverage data integration techniques and algorithms to transition from gold labels to high confidence labels. And again, the key idea is very similar to that of data fusion, which is to actually model the error rate of the different annotators. All we changed here is the notion of a data source, right? Finally, something that is not out there yet, we really need debugging tools for this type of weak supervision models, and we really need to detect bias in these types of weak supervision signals. Any questions on this part? Yes?
So in data fusion, I think you had access to some gold standard to estimate the error rate, right? Here, you don't, or do you?
So here you can use two types of approaches. You either have access to, again, a very small seed that you use to leverage the performance of your unsupervised model. So you rely on an unsupervised model, but you leverage a very small seed just to evaluate the performance of that and to basically detect. You use it to have some rudimentary results for detecting bias. But overall, you can view it as an unsupervised approach for now.
Yeah. So the question is, I don't know if in real world have you asked users to write these rules, are they really precise, are they sufficiently precise to be useful? Because you may end up actually evaluating that the rules tend to be really inaccurate.
So here's the thing. If you have rules that have precision of 1, first of all, that will hurt your recall. And second of all, you really want to have users write noisy rules that overlap. If they're very precise, that is a good thing, but at the same time, if I were able to write rules that are extremely precise, I'd go ahead and use a rule-based system.
Yeah, I should have said accurate.
Okay, yeah, but in practice, users have no incentive. Remember one of the initial assumptions of the data fusion models? On average, we want them not to be adversarial. Users here have no incentive to be adversarial. And in practice, they write good labeling functions. Yeah.
So in the context of text, it is relatively easier to write such labeling functions or rules.
Yeah.
But if you go to more structured data like relational or even graph and XML, how easy or difficult it is to write such rules from an IT?
Excellent question. So for relational data, I will show you an example in a second in the context of data cleaning. That's what we do in the system called HoloClean. You can leverage integrity constraints now to express these weak supervision rules. For the context of, I will call them richly formatted data, the reason is for you to go to the talk on Thursday. You can ask that guy, Sen. The idea there is you want to bring your data in a hierarchical model, a data model where you can reason, for example, about alignment of attributes with headers, about different values being in bold or italics, and so on. Yeah.
How do you leverage crowdsourcing to enable privacy-related data?
This is an excellent question to which I have no answer. Personally, I haven't dealt with private data. I can tell you that some of the applications that the Stanford team had were related to medical data, And there, the idea was they will just deploy the system on their end. That was it. Okay, let's move on to data cleaning. So let's revisit this slide, but now we're going to focus on a different phrase. We're not going to focus on training data, but we're going to focus on manually curating. So we really want high quality data. Why? Because you want to avoid being somewhere there. You want to avoid spending, I'm quite optimistic here, 60% of your time on cleaning data before feeding them to your machine learning algorithms. So data cleaning is actually very closely related to data integration. And one instance is data fusion, right? And the whole idea is, can we actually use some of these techniques to get higher quality training data for our downstream machine learning methods? Again, data cleaning actually started with a very seminal paper that many of you, I hope, know. So the first one to talk about errors in relational data was COD. There it was the big question of how can we handle null values? What are the semantics of null values? I dare you to actually go and train a logistic regression model where you have missing values and come back and tell me what are the semantics of null values when you're training a machine learning model. So after that, in the 80s, we had a bunch of techniques coming up like integrity constraints. The whole idea there was to leverage domain expertise of your designers to actually describe integrity constraints that should hold for your data to guarantee consistency and reduce redundancy, right? You have functional dependencies, multi-valued dependencies, and so on. In the 90s, we went into the ETL world and the world of warehouses, and we started having manual approaches to actually go and transform the data. And finally, after the 2000s, there is this entire focus on repairing errors. And to repair errors, what one does basically leverages all these domain knowledge captured in these different various forms. So you can detect missing values and leverage some statistical information from your data set to go and impute these values. You can leverage integrity constraints to actually go and find violations in your data and try to fix them and so on. And there have been lots and lots of work that I'm not citing here. So the question is, where are we today with respect to to ensuring high quality data? In fact, in the area of data cleaning, machine learning and statistical analysis are actually becoming more and more prevalent. Data cleaning itself, you can split it into two tasks. Error detection, view it as a diagnosis of a problem. There, for example, you have anomaly detection techniques. You may have Bayesian analysis over your data. You might have streaming data and you have outlier detection, right? And then the second task, once you've detected problems with your data, you want to actually go and repair, treat your data. So there we had classical machine learning approaches that leverage models like naive Bayes and logistic regression. More recently, we've seen techniques like boosting that leverage ideas from domain-specific transformations and try to perform on-demand cleaning. And finally, we have weakly supervised machine learning models for performing data cleaning, specifically the HoloClean system. So let me talk about some of these ideas. So the first one I want to mention is that of error detection in the context of a project from Stanford called MacroBase. The whole idea there is that you actually have streams where you have a bunch of relational data being your features that are used for downstream prediction, right? And the idea is you want to actually find errors or problems with your data. How do you do that, and how these errors will affect your downstream predictions? You want to identify anomalies that matter, if you will. To do that, you need to find the most informative features. You want to find the top K most discriminative features. And the whole idea, MacroBase actually introduces this sketching technique called weight median sketching to actually sketch what the classifier trained over the input data looks like and try to identify discriminative features. This is for detection. For repairing, I mentioned boost clean already. The key aspect of boost clean is that actually it leverages these domain-specific detection and repairing rules think of, I have my ETL rules, and I want to clean my data, but I don't want to clean it just for the sake of cleaning. I want to clean my data enough so that my downstream machine learning task performs very well. So the idea here is you combine ensemble models with a downstream classifier, and basically you perform on-demand cleaning. And finally, some advertisement here. You can download HoloClean and play with it. What is HoloClean? It's basically a scalable machine learning, a weakly supervised machine learning tool for data enrichment tasks. One of them is actually repairing. The whole idea there is that you want to build a probabilistic graphical model that captures the distribution that governs your input data. What are different aspects of that distribution? The first one is that you can treat each cell in your database as a random variable, right? Then you have value co-occurrences capturing statistical properties of your data. And finally, you have information coming from integrity constraints that capture invariances that should hold over your data. You can represent that distribution using a factor graph model. Now, the problem is that if you want to apply this technique to actually, like if you want to use learning on inference here, to use this distribution to predict what the value of a cell should be, so to fix errors in case of erroneous cells, this won't scale. To do that, I won't go into the details, but we perform some relaxations of those constraints just to make sure that things scale. I'll be super happy to take that offline for the interest of time. It works. It works really well. And it works well because actually it captures the fact that in reality, remember again this, on average, we're not in adversarial scenarios. More recently, this leads to new theory, but I'm going to skip that and go to the challenges in data cleaning. So what are the challenges? Error detection is still a challenge. We are really good at capturing errors with respect to formats, typos, misalignment, and so on, but we don't really have really good machine learning solutions for error detection. And tuple-scoped approaches, this is my term for what Trifacta does, seem to be dominating. We need to leverage those techniques for efficient error detection and extend them. And the other idea is deep learning here useful or not? We need a formal framework to actually describe when and how we can automate data cleaning solutions, when there is no hope to perform automated cleaning, but we really need to bring in humans. And also another thing here, again, and one of the major bottlenecks is collecting training data. So we have some initial results on how to use integrity constraints to have weak supervision setups, but more work is needed here. And there are very few end-to-end solutions. Okay, recipe. Detect and repair your data. That you need to do to guarantee high-quality input data for your machine learning algorithms. Machine learning can partially automate cleaning. You need expertise, domain expertise, to actually make this happen. Scalability is a big issue, and we really need more end-to-end systems. Okay, in the last few minutes, let me just conclude and describe briefly some research directions that we find quite exciting. So we talked about data integration and machine learning being a natural synergy. So from the perspective of data integration, really data integration is one of the oldest problems in data management. And transition from logic to probabilities with the seminal work of Feleghi and Sanders actually revolutionized data integration. All the work being done after that, using probabilities, allowed us to reason about the inherent noise in data that we have. This is very similar actually to the revolution that happened back in the 80s in AI. We moved from rule-based systems to probabilistic systems. And we saw in many cases that modern machine learning techniques, random forests, deep learning, right? They actually have the power to streamline many tasks that are related to data integration. On the other hand, from the side of machine learning, data is the bottleneck of modern machine learning approaches. And deep data integration related methods and algorithms actually have changed the way supervision, the collection basically of training data, is performed. Weak supervision is a paradigm that is here to stay. And beyond that, we actually need to think of how can we leverage other ACEs that we have in our sleeves. For example, we have done extensive work as a community in catalogs, right, data cataloging, and how can we use these ideas to lead to cheaper collection of training data. Okay, so opportunities. What can we do? The first thing you need to ask yourselves is, do we need a monolithic system? Do we need to go back to our well-known relational database management system, or do we need an ecosystem of tools that can be used to actually solve the problems of data integration? How can we bring in humans in the loop effectively? How can we do that? What is the right approach to actually inject domain expertise? Another idea that, another direction that hasn't been explored fully is what happens with multimodal data. When you have information coming from diagrams that are basically images and tables and text at the same time for the same entity, how can you leverage that in a single data integration model? Maybe deep learning is the answer here to actually perform multimodal data integration. And then another thing that we didn't really talk about is I trained my model. I want to deploy it. My model is a random forest, and I need to generate features that have to do with similarities of attributes that correspond to distance, string similarity distances. These are very expensive features to compute on the fly. So one question is, how can we actually serve these models efficiently? For machine learning, of course, back to data catalogs, data augmentation actually relies on transformations, but at the same time, we can start thinking of data augmentation across different data sets. We can start reasoning about how valuable data is for machine learning applications. And finally, there is a huge effort in the machine learning community to come up with benchmarks for their machine learning models. The most recent one is this effort, MLPair, from different companies and different universities. They have a prime example of data integration where every researcher is actually requested to file a pull request on GitHub with a data set to collect data. So it's manual data integration to actually build the benchmark. Okay, just to summarize and conclude, this is the last slide, I promise. Basically, data integration needs machine learning if we really want to automate many of these tasks. If we want to streamline data integration, we should and use machine learning. In many cases, we actually have production-ready solutions. There's lots and lots of more research that needs to be done for certain tasks of data integration. And for machine learning, all we need is data. The software 2.0 stack is data hungry, and we need effective solutions to feed it. With that, I would like to thank you. I would like to mention that our slides and the list of references will actually be available soon at this website. It's very easy to remember, dataintegration.ml. Thank you.
So we will take questions offline so the next tutorial could set up. And thanks a lot for coming.
Thank you.